Okay, I'm going to try to make this as short and sweet as I can just to get us started on Chapter 7, and then we'll dig in a little deeper when I get back on Monday. So we've already met one model in this class, and that's the normal model, which does a reasonably nice job of taking a unimodal symmetric histogram or dot plot, putting a curve around it, and doing approximations to solve problems like what percentage of the people have below a 28 on the ACT. So models are those lovely perfect world curves that just, it's what we wish was true, but it isn't really true because real world data is messy. But it does a pretty good job of predicting how the real world is going to behave. So in Chapter 7, we meet our second model. The model being that, picture perfection of what we wish things could really be. So we've talked about correlation. We know that correlation tells us the strength and direction of a linear set of data, linear scatter plot. It tells us that, but it doesn't actually describe the association in terms of how X can lead to Y. It doesn't give us a way to do predictions, and that's what we're kind of fishing for. Is we want a model, we want an equation, we want to know what this line looks like that models how these points behave. So the what is a linear model. It's a line. So a linear model is an equation of a line. We want to know what the line is. Not just that there is a line, not just what it looks like, but we want to know that line. Because that line could be useful for making predictions. The line we use will never contain all the points. Because in the real world of statistics, things don't ever line up perfectly. They just don't. If they line up perfectly, you enter the world of algebra, where the guy is moving on the bicycle at a constant rate of speed on a horizontal surface with no interruptions. Yeah, that just doesn't exist. No bumps to the path. So a model is a perfect world picture of what the messy real world data does. So we use the model because the real world data is just a little bit too messy to deal with most of the time. So the model itself is called a regression line. So we've seen that terminology already just fishing through some buttons on the calculator. There are two different standard structures for regression lines. One is the version that we learned in algebra class. It's the y equals mx plus b form. That one you're already familiar with. M is the slope, b is the y-intercept. Sometimes the y-intercept has no purpose at all, no real-world context that makes sense, but it still exists. And then there's the stats version that isn't even the one that the calculator has. The calculator has a version that says y equals a plus bx. It's a little more similar to this second one, but it's still not quite the same notation. So just because statisticians kind of worked in their own little world for a long time, and they still kind of do, they're kind of outcasts amongst the breed. They use their own version of notations for lots of things, one of them being this notation for the regression line. So b sub 0, or sometimes we call b naught, N-A-U-G-H-T, naught, like nothing, is the y-intercept. So this, or sometimes we just call it the intercept. And then the b1 is the slope. And when we dig in a few days to the formulas in the Blue Book, we're going to find that that's the notation that we see in the Blue Book. So that's the one we really have to be familiar with in this class. So b sub 0, think of it as the y when x is 0. When x is 0, that's what y is. So that's why there's a 0 involved. And then b1 by default would have to be the slope. Notice that there's this little hat looking thing sitting on top of the y's now. That's there because it's a model. Models get special treatment because they're perfect world things, not real world things. And in the world of statistics, linear models, the only ones that this works for, linear models get a hat on the y's. And we call it the predicted y. So we don't just read this y, we read it y hat, or we read it predicted y. So let's just make a note. This is y hat. That's what we call it. Y with a hat on, but y hat for short. Predicted y, it's a few more syllables, but that's what's really going on. So it's a y, we can predict a y using the mx plus b or the b naught plus b1x. So just some notation issues that we're going to have to deal with. Now, let's say we have a set of data, And we decide that when we look at a picture of it, it's reasonably linear, doesn't have any terrible outliers, and we want to make a model to do some predictions. Okay? There's some conditions that have to be met before you really are supposed to even make a model. Like with the normal model, you have to start with a histogram or a dot plot or a stem and leaf plot that is reasonably unimodal symmetric. If it's not unimodal symmetric, a normal model is not helpful for doing predictions. In the same way, if you don't meet certain conditions, a linear model is not helpful. First of all, you have to have quantitative variables. That's kind of the no-brainer. You can't make a scatter plot if you don't have quantitative data. So if you don't have a scatter plot, you certainly can't draw a line through a bunch of points. So that's kind of the have to have quantitative. The straight enough condition says that the scatter plot has to be reasonably straight. If you have a big fat curve in your set of data, it is not appropriate to stick a line through it and say that line does a good job of describing what those points do. If you have outliers that could influence the fit of the line, that's a problem. It's going to throw your model off. So to get a good model, you're either going to have to lose the outliers, like get rid of them altogether, or decide to not do the analysis with the model after all. And last but not least, this is kind of a new idea, is called the plot thickens condition. The spread around the spread of the data from left to right needs to stay fairly consistent. So another way to say this is we want no fan shapes. So if I have data that starts out pretty compact around the line, and I don't know if I can draw dots very well or not, and as it goes toward the right, it spreads out, and we get a set of data that looks like that, and we try to put a line through it. Okay, the problem is the farther you get to the right, the less predictability you get, because the scatter goes from tightly packed to spread out, so you get what I call a fan shape. So that's a fan shape. Fan shapes are bad because they really aren't appropriate for a line to go through them because there's so much spread on one side. If you get the mirror image of that and it's really, really spread out on the left and then tightens up on the right, it's the same deal. It's still a fan shape, and that's not good. That's not appropriate for a linear model. So you really want a nice, as compact as you can get, straightish bundle of points that you can put an oval around. The longer and skinnier the oval, the better it is. There are 3 ways to get a regression equation, 3 ways to actually get that model once you decide that it's appropriate to have a model. One is to let the calculator find it. We've already played with that a couple of times. We're going to come back to that later, not really deal with it any today. But the calculator will run the regression analysis. You can actually drop the equation on the graph on your calculator and then just copy it down. Or you can run the regression analysis in the spreadsheet and then copy it down. So we'll come back to that another day. The second way is to get a computer statistics package to generate output that has the model on it. So basically it's the same thing the calculator's doing, except that we don't actually have those computer programs here. College professors typically use computer packages for statistics instead of calculators. And so one of the things that they want us to be able to do on the AP exam is to read computer output from some particularly popular packages that are used pretty often in the statistical world. We need to be able to take computer generated output, read it, glean the important numbers from it, and then do the analysis with those numbers. Looks a little bit different than what our calculator feeds us, so we just have to learn to read it. That's what we're going to tackle today. And then the third way is to actually use the summary statistics. So if we have a list of things like means and standard deviations and R values, we can write that equation by hand. That'll be the last thing we learn to do. So we're going to deal with this middle one for today. And to do that, we're going to pull out an old AP exam question from 2011. It's really, really small and hard to read on your paper. I apologize for that, but we'll get the gist of it anyway. So this one's a windmill problem. Windmills generate electricity by transferring energy from wind to a turbine. A study was conducted to examine the relationship between wind velocity wind velocity in miles per hour, and electricity production in amperes for one particular windmill. So it sounds like the X was wind velocity and the Y was electricity. I'm just going to abbreviate. So I'm just going to take some notes as I go on the side. You can always do that on exam day. For the windmill, measurements were taken on 25 randomly selected days. So I'm going to make a note over here, n equals 25. That's how many data points we collected. And the computer output for the regression analysis for predicting electricity production. Okay, there's really the kicker right there. Electricity production is being predicted. Whatever's being predicted is the Y. The predicted variable is always the Y. So I'm absolutely sure now that the X is the wind velocity and the Y is the electricity. So we're using the wind speed to predict how much electricity is getting generated. So predict electricity production based on wind velocity. The outputs given below. The regression model assumptions were checked. In other words, they looked at their data. They were quantitative. They decided that the picture was straight enough. The plot didn't thicken. And there were no outliers that would mess with the regression. So when they say the model assumptions were checked, they checked to make sure that it was appropriate to make a linear model. And determined to be reasonable over the interval of wind speeds represented in the data, which were from 10 miles per hour to 40 miles per hour. So they only looked at wind speeds that were sort of typical for that area, probably. And then this is the computer output. It looks quite different than what we're accustomed to looking at on the calculator, so we have to learn to read it. So let's see what we have here. We have right here COEF. That means coefficients. Coefficients are numbers in front of variables in algebra. That could come in handy. And then over here on the side, I have two things that are important. One is a constant. A constant means a number without a variable. So if it says constant, that means it's a y-intercept. Because in a linear equation, the constant is the number that's not in front of an x. And the wind velocity, so that's x. Oh, the wind velocity is x. Yeah, it sure is. Okay, so let's see what we got here. Constant, the coefficient of the constant, which is just a constant, is 0.137. That's actually b sub 0. That's the y-intercept. Wind velocity is x. This next number, 0.240, is the coefficient of wind velocity, the coefficient of x. The coefficient of x is the number in front of x. That's your slope. So that's b sub 1. That's the slope. So this number is the intercept. This number is the slope. Everything else on this page, ignore for now. The only other thing on here that you have a clue about at this point is r squared, which is actually the square of your r value. You don't really need it. Don't worry about it. You need to pluck two numbers out of here, a slope and a y-intercept. Fortunately, they're usually in the first column of numbers. And almost always, the intercept is on top and the slope is on the bottom. So we just need to learn to pluck those numbers out of computer output. We're just going to get some practice of that. Part A. Use the computer output above to determine the equation of the least squares regression line. That's a fancy word for a regression line. Identify all variables used in the equation. Well, I have two variables. I have wind velocity and I have electricity. I've got two choices for how I define those. I can identify those separately and say x is wind velocity, y is electricity. Actually write it out. And then I can give the equation, or I can actually put the context in the equation itself. So I could do y hat equals b sub 0, which is 0.13, I can't read it, 0.137, I've covered it up, plus b sub 1, which is 0.240 times x. Okay, I need a hat on it because it's predicted electricity, not the actual electricity output. Is what the model is going to predict the electricity is for any variable x, for any value of x. Now, the problem with this equation is it only is going to get you a partial on this part of the problem because I haven't identified variables using the equation. The better version is, instead of y hat, to say electricity and put a hat over it. It's a big hat, but it still works. So we're going to read that as the predicted amount of electricity equals 0.137 plus 0.240 times wind velocity. I'm just going to make it all one word. It's best if I do it the second way because I kill two birds with one stone. I nail down which variable's which, and I get the equation at the same time. That's the preferred version, although this first one will work as long as you define your variables on the side in addition to it. Part B. How much more electricity would the windmill be expected to produce on a day when the wind velocity is 25 miles per hour than on a day when the wind velocity is 15 miles per hour? Show how you arrived at your answer. Show how means you have to show work. So maybe we'll do this one the long way. I want the wind velocity on the 25 mile per hour day. I want to know how much electricity is predicted. Okay, so y hat predicted y. Make sure the hat's on. Without the hat, it's wrong. They're going to dock you down to at least a partial. Y hat equals 0.137 plus 0.240 times 25. Okay, that's going to give me the predicted value for 25 miles per hour. Alright, so we're going to need a calculator for that. 0.13, I lost my calculator. Should have already done this in advance. Let's add a calculator page. So 0.137 plus 0.24 times 25 is about 6.137 amperes, whatever they are. Okay, and then we're going to do the same thing. Y hat equals 0.137 plus 0.240 for 15 miles per hour. And so I'm going to just back up and change that 25 to 15, save myself some typing. And that's going to give me 3.737. 3.737. And the real question was how much more electricity, so we need to find the difference of those. So if I subtract, I'm just going to use my calculator here because that's faster than me trying to do it in my head and I'm less likely to make a mistake. I get 2.4. So 2.4 amperes more is my final answer, and I've shown my work to back up my answer. You also could, if you haven't already figured it out, and some of you already decided that I did this the longest way possible, you could subtract 25 minus 15 and know that there's 10 miles per hour more, and then substitute 10 in here, and when you get finished computing that, does that give you the same thing? I don't know if that gives you the same thing or not, does it? I might have just goofed. No, that's something different. Never mind. This is how we need to do it. Okay, part C, before I say anything else crazy, let's do part C. Last thing we need to be able to do for today is to correctly interpret slope and intercept in context. And that's the last couple parts of this question. So when you describe slope, you need to make sure, of course, that context is there. And the key is to describe how the y changes in context with units as the x changes by 1. So you're thinking slope is change in y over change in x. Your slope is always going to be a decimal number in statistics class. So your decimal number on top over and understood 1 would mean how y changes is your slope, your top number, over 1 unit. It'll make more sense when we actually do it. We want to include some keywords. The model predicts. Always imply that it's a prediction. It's not what really happens. It's what we would like to have happen if the data were just in a perfect world. And then on average is a good thing to throw in there as well. And when we get to the intercept, we're going to describe what the predicted y is. Make sure that word predicted is there when the x value is 0. And make sure your units are there and the context is there. It'll make more sense when we actually look at a problem, though. So you can come back to this if you need to for just some specific structure. So for the problem we just did, we want to interpret the meaning of the slope. So the slope was 0.240. Okay, so I'm going to make some notes to the side first. Slope was 0.240, and I know that slope is change in y, which is change in electricity, over change in x, which is the wind speed, wind velocity. To make 0.240 a fraction, I need to put it over 1. So that means we're having a change in electricity of 0.24 amperes over 1 mile per hour. So for every mile per hour faster the wind blows, because it's positive 1, we have a positive here, the electricity produced is going to increase by a predicted 0.240 amperes. Now I just have to put that in words. I always like to kind of do this on the side, and you always talk about y first, or always talk about x first. As x does something, y does something to respond to it. So I'm going to start with the model predicts. It's just a good way to start, so then I make sure that I communicate that it's a prediction, not reality. The model predicts that for every 1 mile per hour increase in wind velocity, the electricity produced increases by an average, squeeze that word in there, of 0.240 amperes. This is again one of those sort of cookie cutter sentences that if you kind of learn the structure, you can write it the same way every time. You're always going to have a change of 1 unit in your x's, and your y's are always going to be whatever your slope is, the change is. And if it's a negative slope instead of a positive slope, the only other change here is this second half changes to it decreases by an average of whatever. So you need an increase and a decrease if it's a negative slope. The last one's easier. Interpret the meaning of the intercept in context for the windmill problem. Okay, well, the intercept is 0,0.137, where 0 is your wind velocity, so that's miles per hour, and 0.137 is amperes. So, if the wind velocity is 0 miles per hour, the predicted, I could spell, the predicted electricity production is 0.137 amperes. Make sure you get that predicted in there. You also could say if the wind isn't blowing. That's another way you could phrase it. Means the same thing. Okay. Practice, practice, practice. You have an assignment on the next slide. Take a whack at that, and I will see you on Monday.